In this lesson, we're going to review the Open Shortest Path First Protocol, or OSPF. OSPF dynamically creates and maintains routing tables on each router, and then determines the shortest route to each subnet in the network. OSPF is scalable on very large networks large enough that it's not logical to manually create, maintain, and update routing tables. OSPF creates and maintains these routing tables using three processes: neighbor discovery, topology exchange, and route identification. Let's start with neighbor discovery and topology exchange to see how this works on a small point-to-point network. We'll start with these two routers. Each router has already been assigned a router ID, or RID. The one on the left has an RID of 1.1.1.1, and the one on the right has 2.2.2.2. It's critical that routers are assigned RIDs. We'll just assume that these RIDs were manually configured. A data link has just connected these routers, and they don't know about each other yet. Becoming neighbors with connected routers is the first step in OSPF. Each router immediately sends out hello packets, looking for connecting routers that have OSPF configuration information. In this scenario, router A sends a hello packet with its OSPF information, and it basically says, "Hello, I'm 1.1.1.1, and I am here." Router B receives this and checks the OSPF configurations. If it matches its own OSPF configuration, it replies with its own hello packet saying, "I've seen 1.1.1.1, and my router ID is 2.2.2.2. This is called the init state. Next, router A replies saying, "I've seen 1.1.1.1 and 2.2.2.2. Once the two routers know about each other and establish matching OSPF configurations, they move into the two-way state. Now they start exchanging link state database information. You'll want to note that matching OSPF configurations means the routers must be in the same OSPF area, which is area 0 in this example. They also have to be configured with the same hello interval, which is 10 seconds by default, and with the same dead interval, which is 40 seconds by default. Other information is included in the hello packet, such as its priority, the RID for the designated router, the RID for the backup router, and a list of that router's other known neighbors. In this two-way state, OSPF routers start exchanging database information and begin in the X-start state, where they negotiate how the data will be transferred by establishing which router is going to be the master and which router is going to be the slave during the exchange. Once that's decided, the routers move into the exchange state, where they each receive a description of the other's database and identify new information to add to their own databases. Next, the routers move into the loading state, where they exchange LSUs, or link state updates. LSUs include LSAs, which are link state advertisements. Both routers end up with a complete, full database. Now, the routers are in the full state, and they know the topology of the network they belong to. From this point on, they'll monitor each other using hello messages. LSA messages are sent out to keep both routers up to date. This scenario only works if we have a simple point-to-point connection between two routers. If we have a multi-point network, OSPF works differently. We want to minimize the database traffic exchange caused by LSUs and LSAs. OSPF uses a designated router, or a DR, to do this. Non-designated routers only exchange information with the DR, not with each other, minimizing database exchange traffic on the network. The router with the highest OSPF priority becomes the designated router. You can manually decide which router will be the DR by configuring the OSPF priority. If you don't, or if there is a tie for the highest priority, then the router with the highest numeric router ID becomes the designated router. The router with the second highest priority is selected as the backup designated router, or the BDR, which monitors the DR and takes over if it goes down. Another key difference with a multi-point network like this one is that there are two stable OSPF neighbor states instead of just one, like the one we saw with the point-to-point connection. Now, the DR and the BDR are in the full state, fully adjacent. That's because they've completed the exchange process that we talked about earlier. In the full state, they both have and maintain the same link state database. The routers that aren't the DR or the BDR don't communicate directly with each other. They know that they're neighbors, but they don't exchange database information with each other. They're not in a full state. They stay in a two-way state, and they only exchange database information with the DR. That's it for this lesson. In this lesson, we reviewed how OSPF works. First, we looked at how neighbor discovery and topology exchange works. Then we went over the roles of the designated router and the backup designated router to see how database traffic exchange is minimized.